Welcome to my YouTube channel. Dhanesh here. So in this video, we are going to discuss about neural network. This is part 2. In the part 1, we covered the architecture of the neural network. So we understood like artificial neural network is a computing system inspired by biological neural network and our brain. Our brain contains trillions of neurons and they connected together and they communicate each other. So all these things, we are trying to mimic in our artificial neural network. So in this part 2, mainly we are going to discuss. See, I can show you another important aspect. See, these are all the 7 sections we are going to cover as part of the neural network. Model architecture. In the first video, we covered the model architecture. Now, in this video, we are representing the mathematical representation of this neural network model. How do we mathematically represent this? Then about activation functions and bias nodes, cost function, forward propagation algorithm, then backward propagation algorithm. So these are all the 7 aspects we are going to cover as part of this neural network. See, in the second video, we are going to cover the second part, that is the mathematical representation of this neural network. See here, to understand this neural network, its mathematical model, we are going to consider a simple neural network model. It's the simplest one we are going to consider. This model is having 4 input nodes. See, whatever model we are going to discuss is having, I can show you the model. This is the model we are going to use it here. It's having 4 input nodes, x1, x2, x3, and 1 bias. Plus 1 represents the bias. See, weight and bias. These are all the 2 terms coming into picture in neural network. In the most fundamental way, I can tell you, in the equation of a straight line, y is equal to mx plus c, where m is the weight of the network and c is the bias. So that is the simplest explanation I can give you for weight and bias. See here, the input layer, it's written here. This is the input layer. It is x1, x2, x3 and plus 1. That is, this is 4 nodes with a 3 plus 1 bias. So that is the input layer. And 1 hidden layer. We have the hidden layer. See, in the last video we discussed, in the input layer we are giving the inputs. In the hidden layer, all computations, all calculations are happening in the hidden layer. So it is represented as, since it is, second layer, so we are having in this model only 1 hidden layer. So there is A12, 2 represents the second layer here, A22, the second node in the second layer, A32, the third node in the second layer, and this one again, a bias, plus 1 represents the bias. And A13 is the output layer. So this represents the output layer here. So this is the output layer. See, and you have the output, and it's a function of x. The output, it is a function of h. Output, we are representing it as h. It's a function of x, and it depends on 2 variables, theta and b. Theta is the weight of the network. The weight is denoted by the letter theta. Sometimes W also we will use. B is the bias of the network. So H, theta, comma B, and it's a function of X. So this is the figure it represents. So input layer, output layer. See, output layer, I have explained in the hidden layer, all the computations and the calculations happens. Then the input nodes can be placed in one vector and the nodes from the hidden layer we are going to present in a vector A. So this is the representation. All the input nodes we are putting it in a matrix. So you know the concepts of matrix and determinants. The value of a matrix is determinant. Matrix means simply the arrangement of data in rows and columns. So you have x is equal to, you have x0, x1, x2, x3. It's given here. So this is the input node. So input node we are representing in the vector x. This is a vector. See, we won't call it as a matrix. Here we call it as the input vector. So the input nodes are represented in the input vector. It's a very important. I can tell you the input node is represented in the input vector. So it is just 1 second. That is I can tell you that is vector x. Input node we are representing it as vector x. So this vector is represented in this form of, this is vector x. X is equal to x0, x1, x2 and x3, and the nodes from the hidden layer is given in the vector A. So if you are familiar with physics and mathematics, you might have heard of scalars and vectors. So vectors, it's having both magnitude and direction. That is the physical interpretation of vector. But here in machine learning, we call this this matrix as vector x, and this as vector A. The hidden layer we are calling it as vector A. You understood this. So again I told you the weight of the network. Again I am telling the most fundamental explanation for weight and bias. If you want, I can tell you it is in the line. You have a line y is equal to, let me take the equation of a straight line, y is equal to mx plus c. This is the equation of a straight line. See, in this equation, if you take we can write it as mx plus c. Here m is the weight of the network. This is the most simplest, it is the simplest explanation for the weight and bias. C is the bias. What is C in this equation? C is the y-intercept. M is the slope. This is the slope. This is the intercept, y-intercept. So I told you about weight and bias. Now weight is denoted by the letter, you can tell it as weight is denoted by the letter W, weight or theta. Here we are weight, it is denoted by, here we are using the letter theta. Weight is denoted by the letter theta. So the weight between input and hidden layer will represent 3/4 matrix. Is it right? See, weight, in the last video I told you the black arrows in the model. See the last picture. If you want, I can show you that picture. In the last video I can show you that picture, just 1 second. See, this is in the last video, this is the picture we used for the neural network model. This is the architecture. Here you can have the red circles represents the input layer. Here we have hidden layers. See, in the model currently we are discussing, it's having only one hidden layer. So in this model you can see it The output layer, it is black circles. That circles represent a node. And there are two hidden layers. One is the blue and the green is the second hidden layer. And you need to understand here, like this black arrows, it represents the weight of the network. See, each node is connected with the next node in the next layer with a black arrow, and it represents the weight. And weight, I already discussed you, weight is the impact of one node on the other node in the next layer. So that is the explanation I have given you in the last video as well. Weight is the impact of one node on the other node. The next node can be in the other layer. So that is the weight. That is the weight in the proper definition. So from the equation of the straight line, I have given it is the most fundamental explanation for weight. But from a neural network perspective, weight is the impact of one node on the other node. So weight, it is denoted by the letter W, and here we are discussing, here in this, here we are using theta as the, weight of the network, and the weight between the input and hidden layer. See, our model, currently we are using this model for the mathematical representation. This is the simplest one. Here the difference is, here we are having only one hidden layer. So there is the arrows between the input layer and the hidden layer, that is the weight. And you can see again the arrows between the hidden layer and the output layer. See, these two weights. So the weights, first I am considering the black arrows between the input layer and the hidden layer. Sorry. So the arrows between the input layer and the hidden layer. See, if you see from the x1, how many arrows are going towards the next layer? There are 3 arrows. It's starting from x1. From x2, you can see it again, 3 arrows starting from x2. So from x3 also 3 arrows. So this, the weight between the input and the hidden layer, we can represent it as a 3/4 matrix. So to us, it is a 3/4 matrix, and this this is the. And one more thing, there is a mistake in this picture. What I have done is I didn't draw the arrows between +1 to A1, A2 and A3. It's not correct. See, let me try. Can I draw it here? It's possible. See, it's just 1 second. It is possible. It's the complete. It's in a different color I am drawing. Sorry for that. See, like that. This is the complete one. See, you may ask why I am not drawing an arrow between +1 and +1. That is between the bias. See, it's not needed actually. See, from the +1, the bias on give to the impact on another bias. See, the bias will give impact on the next node, that is here it is the computation, the activation functions happening inside the hidden layer. So that impact only we need to give. See, bias normally give impact on the next activation functions, not on the other bias. See, this bias in the hidden layer also, if you see the bias in the hidden layer, so that also I am considering this bias. It will also give impact on the next activation function. So it won't give impact on the other layers, sorry, other bias. So that's fine. So this is the complete picture. I in the picture I made a mistake, sorry for that. That's why I couldn't draw the weight by using the black arrow. Its a color is different. Now if you see the weights between the input layer and this hidden layer, this is the input layer we are discussing. We are representing the weights between the input layer and the hidden layer with a matrix form. So it should be, you can see it here, it should be a, see, you need to consider to how many nodes means these circles, to how many nodes here from the input layer it is connected. 3 nodes. We have to start from the second layer always. See, you know the order of the matrix. Order of the matrix gives the rows and columns. First, number of rows and number of columns. See, if a matrix is having, I can show you one example here. See, in this, see, this is a matrix. So how many rows are here? These are all rows. One, this is one row, this is second row, this is third row. So this is how many columns? 1, 2, 3, 4. So the order of the matrix is, this is 3 by 4. How many rows here? 1. How many columns here? 1, 2, 3, 4. This is 1 by 4 matrix. So in the same way, if you consider how we consider the order of the matrix, we need to consider the nodes. How many nodes are in the second layer? See, from here we will start. When we consider the weights between the input layer and the hidden layer, we will consider the nodes in the second layer, then the first layer. So how many nodes are there in the second layer? See, in the second layer we have 4 nodes, but the connection is coming only towards 3 nodes. So it should be a 3 by 4 matrix, because here there is no connection. There is no connection between this bias and this bias. So the matrix will be a 3 by 4 matrix. You understood this? Because in the second layer, in the hidden layer, there is 4 nodes totally, but the connections are coming only towards 3 activation functions, 3 nodes. To this bias there is no connection from the input layer. So that's why the matrix would be a 3 by 4 matrix, and that matrix can be represented as, it is from 1 to, it is like, we can write it as, or theta 1 0, the first bias we are, we have how many connections. So from the first one we are going towards, from the first node we are getting how many connections? In the second layer, 4 connections. So those we are writing it as 1 0, 1 1, theta 1 2, theta 1 3. It simply means there is no significance with this picture. This 1 0 denotes it is first, it is the first row and the 0th column, like that. Some prefix we have given, theta 1 0, theta 1 1, theta 1 2, theta 1 3. But how you got this 3 by 4 matrix? It's like, you have 3 nodes, the connection. We always needs to consider from the second layer to the first layer. So that's why it's a 3 by 4 matrix. Then theta 2 0, theta 2 1, theta 2 2, theta 2 3, then theta 3 0, theta 3 1, then theta 3 2, then theta 3 3. Like that we have given some name. So this represents the weights between the input layer and the hidden layer, and it is a 3 by 4 matrix. Now if you take the again between the weights between the hidden layer, see, hidden layer, now we are going to discuss between the hidden layer and the output layer. So again, we will take from the second layer. Second layer is the output layer here. Output layer. So from the output layer to the hidden layer, so it would be, you can tell, output layer we have only one node, and from the hidden layer, from what all the nodes connections are coming, 1 2 3 4, from 4 nodes its connection is coming. So it would be a, from 1 to 4 it would be a 1 by 4 matrix. Am I right? So it should be a 1 by 4 matrix. So that's why this is the matrix here. Here you have one row. 1 by 4 matrix means one row and 4 columns. So it is theta 1 0, theta 1 1, theta 1 2, and theta 1 3. Why it is, I have given the suffix, sorry, in the top I have mentioned like 2, because it's for the second matrix. It is for the it is for the second matrix. I have given a in the top I mentioned like it is for the second bias, sorry, second weights. For the first weights it is 1, it is 1. For the second weights it is taken as 2. So that in that way we can differentiate it. Even here you can give 1 like this everywhere. So like that we can differentiate between the weights in the first between the input layer and the hidden layer. It is the first weight, and between the hidden layer and the output layer it is the second weight. So we have come up with the matrices. So you understood this. See, now we will calculate the activation nodes. See, activation nodes for the hidden layer. So what is this activation nodes? See, in the hidden layer I have already told you. See, in the hidden layer all the computation and the all the calculations happens in the hidden layer. So such nodes we call it as, you see here, if you want to see it properly, this is the this is not the architecture now we are following. This is a general architecture I have given here. Two hidden layers are there. One is hidden layer 1 and the second one is hidden layer 2. So inside the hidden layer we have the the computations or calculations happening in a neural network is inside the hidden layer. See, this activation nodes. See, what is activation nodes means? It uses the activation functions. So what is activation functions? In a neural network, the activation function defines whether the given node should be activated or not based on the weights, not weighted sum. Because see, if you see here to this node, you can see here to this node lot of weights. If I will explain you from this picture. So this is our node. Let's consider this node. So how many weights are coming? Weights are coming from here, from here it's coming from x1, from x2, from x3, from this bias plus, and also weights are coming towards our activation function a1. See, activation node a1. So the sum of all the weights, that is known as the weighted sum. So in a neural network, the activation function defines whether the given node should be activated or not based on the weighted sum. Whether this node should be activated, A12 should be activated or not, that depends on the sum of the weights coming towards that node. The weights are coming from x1, x2 and x3 and plus 1 towards this activation node A1. So based on that node should be activated. So what is an activation function? In the last video also we discussed, in a neural network the activation function defines whether the given node should be activated or not based on the weighted sum. So the commonly used activation functions are step function, ReLU means rectilinear unit, sigmoid is the most commonly used activation function, then hyperbolic tan. These are all the activations commonly used activation functions in neural network. I already discussed this aspect with you. So these are all the commonly used activation functions. So the commonly used activation functions are, you can understand here, that is the step function. This is one. We will, in the coming videos, we will give more clarity on this step function. Second one is a ReLU. ReLU means it's a simplest one. It's a linear function. If you see y is equal to mx plus c, that straight line, it's a rectified linear unit. So this is ReLU. ReLU means rectified linear unit, like that. So ReLU. Then you have the sigmoid function, the third one. It is sigmoid, sigmoid, sigmoid function. Fourth one, hyperbolic tan. These are all the commonly used activation functions in neural network. Tan, you know, sine, cos, tan. Hyperbolic tan is more complex, so that we will discuss in the coming videos. This is, I can tell you, it is the sigmoid function. It is represented as the equation. If you want, I can give to you the activation function, sigmoid function. It is represented by the equation. I will use another color. It is 1 by 1 plus e raised to minus x. This is the equation. For sigmoid function, it is 1 by 1 plus e raised to minus x. This is the ReLU means it is y is equal to mx plus c. A simple straight line will represent, but in more detail we will discuss these aspects. Step function we will discuss, hyperbolic tan. So these are all the commonly used activation functions. Fine. Now we will come back to our our model. This is the model. In this model we are using only one hidden layer. So this model only we are going to discuss. See, now we will calculate the activation nodes for the hidden layers. See, the important point is, for that, to calculate the activation function. See, the activation function we are representing by the letter G in our representations. We will use the letter G for to represent activation function. The activation function is denoted by the letter G. Activation function. I have given you an idea about activation function, different types of activation functions. It is represented by the letter G, activation function. See, now we will calculate the activation nodes for the hidden layers. See, how do we calculate the activation nodes for the hidden layers? For that, we need to multiply the input vector x and the weight matrix theta. Then we will get the activation function. That's what I told you. The input vector will be multiplied with the weights matrix. So to get the activation node in the hidden layer, this is very important. Multiply the input vector. Input vector should be multiplied with the weights. That is the concept, right? See, that you can the into this is into x. This represents the multiplication. This is I can like this. I will write it. You will understand like this. See, into, so into x. See how you will understand this. See, to get you to make you understand this, I will give you the most simplest explanation. That is, see, if you have the equation y is equal to this, y is the output, mx. Forget about C. C we are taking it as 0. Then how you are getting the output? You are multiplying M. M is the weight. I already told you, no. This is the equation. C. This you are taking it as 0. C is 0. This equation, it should be Y is equal to mx. That means we are multiplying. M is the slope. Slope means weight only. See, M means slope. Slope means this is weight. This is weight. So we are multiplying the weight with the input to get the output, the activation function. In this case, the next node is the output hidden layer. That is the activation node. That is the output. So that is the simplest equation that is coming into picture everywhere. So this is the concept. See, the input vector I told you. So this is the explanation I am giving you. To calculate the activation node for the hidden layer, we need to multiply the input vector x and the weight matrix theta. Then we will get the activation function g. And then apply the activation function g. See, activation function we need to apply, that is sigmoid or a function. We will have to apply the activation function here. See, here you will get the activation node. To that you need to apply the, I will give you a clear idea. This is a important concept. Just one second. See, what I am telling is to get the to calculate the activation node, you need to multiply, input vector with x, because the equation here you have is y is equal to mx. This is the equation of a straight line. Here we have taken c as 0. Here m is, in the most fundamental explanation, is m is the weight of the network. So if from this you understood, to get the activation node, you need to multiply the input, that is activation node means the output y. To get the activation node, you need to multiply the input vector x with the weight. Weight here we are taking it as theta, right? So theta into x. So theta into x. So this is the, then we need to, here we have activation functions. So activation function is denoted by the letter G. We need to apply the activation function to this product. So this is what we usually do across all the neural networks. This is the simplest equation. This is very important. G is equal to theta into x. How you got theta into x? From the equation of a straight line, mx, weight into input, that is the output. To that we are applying the activation function g. Sometimes we will use this letter as well, sigma, for activation function. You can use g or sigma. Both represents the activation function. I have told you what is an activation function. Once again I am repeating it. See, the activation function, in neural network, the activation function defines whether the given node should be activated or not based on the weighted sum. Commonly used activation functions also we discussed. So this is the way the things will come. So then the activation function, then we can write the activation nodes in this form. We can come up with these equations based on this. See, theta into x. See, the first thing, theta 10 into x0. x0 is the first input. So for the a1, see, your model, you can here see this is a12, this is a22, this is a32. So a12 will be, the first node will be g of theta 10 1 x0 plus theta 11 into x1 plus theta 12 into x2 plus theta 13 into x3. In the same way, a22 will be g of theta 201. See, g is the, we are applying the activation function. First you need to sum the these products I told you here, right? Theta into x. so that you need to sum everywhere. So you will get theta 2 1 into x1, theta 2 2 into x2 plus theta 2 3 into x3. To that you apply the activation function g. In the same way, a32 will be g of theta 30 into x0 plus theta 31 into x1. See, this one represents for the first weighted sum. So sorry, the weights for the input layer and the hidden layer. The weights for the hidden layer and the output layer will be represented by this 2. In the top you have 1 1 1 everywhere. So 1 1 1, this one I am talking about, this one everywhere. So this one represents between input and hidden, that is for this one. 2 will be used for between hidden and output. That's all. It's really simple. So like that you can come up with the equations for A32. In the same way, for the output, that is between the hidden layer and the output layer, again if you see the model, here it is the output is denoted by h. Here it is a function of x. So normally we will take the letter y as the output. Here we have taken as h. See, y, it's a function of x and it depends on two attributes. Theta is the weight and b is the bias. So that can be represented by the equation. By this equation, you can see it here. It's 1 second, sorry. This is the equation, h theta x. See, we have, it depends on the weight. We neglect, see, in the simplest form we are writing, we are not considering for the time being the bias. H theta x is equal to a13. If you see the architecture here, see, this is A13, this is the node. So in that node only you are getting the output h of, see, this one bias we neglect now. So for the weight it is h theta x should be, you can write it as h theta x, that is A13 is equal to g of theta 2. See, this 2 here, everywhere you have 2. This 2 represents, for in the case of theta, that weight between the hidden layer and the output. Theta 2 for the hidden and output. For the input and hidden, it is theta 1. So again you are multiplying theta 10 with A20, theta 12 with A12, theta 12 with A2, theta 13 with A3. Then you apply the G is the activation function. I told you, you have to apply the activation function for a neural network. So that is a really important thing. In neural network, the activation function defines whether the given node should be activated or not based on the weighted sum. So that we need to consider. This multiplication is the simplest way. Y is equal to mx plus c. That is, the output is weight into the input. This is the most simplest. Weight into input. That is the simplest concept. But in neural network, one more extra things come into picture. To that you sum it and you need to apply the activation function. That is the thing coming into picture in neural network. So this is the equation. This is the most important equation for the output. So this is the simplest mathematical model for a simple neural networks. Here, this is the figure we used. We used only one hidden layer. One input layer. This is the maths behind the neural network. But how do we apply this math and backpropagation, all this? It's really interesting. So in the coming videos we will cover. So these are all the portions we need to cover. We covered only two aspects now: model architecture and the mathematical interpretation of this model. Now I am explaining you different types of activation functions. What is the bias node? Then cost function, we will how the cost function works here. Then the forward propagation and back propagation algorithm. It's really important here. See, all these aspects we will be covering in the coming videos. This is the second video about neural network. So thanks for watching.